the introduction. It's my great pleasure to talk about our work called the Path Development Network for analyzing sequential data by exploiting the finite dimensional Lie group representation. So if you have any question during my talk, please feel free to send the question via the chat or just raise your question. So let me start with the motivation of our work. Time series and or sequential data are ubiquitous nowadays. Examples range from the financial time series to the human action motions. It's very useful to develop an accurate, efficient, and robust algorithm to extract the useful information from the sequential data. For example, in finance, people are interested in predicting the future market movement using the historical financial time series information. And in the slides, there is also the example of the skeleton human action sequence. In this case, we would be interested in predicting the action class label from the action sequence. In this talk, I would not distinguish the discrete time series and the path. In practice, time series are often observed as the discrete time points, and we will embed the discrete time series to the continuous path. The path means a function with respect to time. So by doing so, we allow the unified treatment of the discrete time series of potentially irregular sampling of variable length. Also, this continuous times view of treating this time series is more well suited to the high frequency data. And the examples of the financial time series forecasting or the skeleton-based action classification actually all belong to the supervised learning, while the input is a path. So let me quickly recap the framework of the supervised learning. So the goal of the supervised learning is to learn the functional relationship between the input and the output from the collection of the data samples. And let's focus on the regression setting where the output space is RD. So how can we solve this supervised learning on the path space? So the general framework is that we will assume that the output is given by certain mean function, deterministic but unknown, acting on the input and perturbed by certain noise. And the goal is to learn the conditional expectation of the output given the new input. Equivalently, what we want to learn is this mean function f. So usually we will postulate a model, say f theta, fully characterized by the model parameter theta to approximate this mean function. And then we need to propose a loss function to quantify the performance of the model parameter theta. And one popular choice is the mean squared error to quantify the discrepancy between the model estimated output and the actual output. Then the optimal model parameter theta star is obtained by minimizing this loss function. For the simple case, well, the f theta is a linear function. Then we actually use the L2 loss. We can solve this optimization problem analytically, but for more complicated model, we need to use a numerical optimization method to solve it. Once we obtain the estimator of the optimal model parameters theta star, we can use it to predict the estimated outcome given any new input. And we also need to propose the test metrics to assess the model performance. in the most of the nonlinear regression model actually follows the same idea, that is a basic expansion. For example, if we think about the polynomial regression, what we actually do is to transform the input to x in R to the its monomial basis. Then we can employ the linear regression on the monomial basis. So in that way, by transforming the raw input to the features, the universal features, one can reduce the nonlinear regression problem into the linear one. Then the natural question for us to consider is if the input space is a path space, what would be the good basic function on the path space? The rough path theory provides an answer to such question. One core object of the rough path theory is so-called the signature of the path. So it's the signature of the path can be viewed as a non-commutative monomials on the path space. It's defined as the iterated integral of the underlying the path. And it has been shown that the linear functional on the signature are dense in the space of the continuous function on the path space. And therefore, in theory, one can use a linear models on the signature feature for as the non-parametric model for the time series data. And more recently, one can regard the signature as a general layer for the sequential data, which can be inserted in the general neural network as long as the input of the signature layer is the time series. And moreover, the application of the signature feature of the time series in real world application are emerging. So by using the signature feature as a complementary feature of the time series, with appropriate the choice of the modern machine learning models, one can achieve the state-of-the-art result on various tasks. For example, online handwritten character recognition, financial time series forecasting, as well as the substance detection. In particular, the online the signature-based method with the convolutional LSTM can achieve the superior performance of the online Chinese handwritten text recognition, which leads to a popular Chinese input app with millions users usage. However, although the signature has the various good properties, it has its own bottleneck, that is the curse of dimensionality caused by the high path dimension. So the signature of the path is the infinite series, and if we truncate it into the degree k, then the corresponding feature dimension is given by this formula. And here you can see that the dimension grows geometrically with respect to the path dimension. So to this end, we propose a trainable alternative, so-called the path development layer, which capture all the essential information of the signature, but provide the massive dimension reduction benefit. So this is a joint work with my student Han Lou and also my collaborator Siran Li from Shanghai Jiao Tong University. And the codes are available through at the GitHub link shown in the slides. So our approach actually mimic the classical idea of the generating function of the infinite series. So suppose that we have the infinite series, real-valued series xm. So how can we encode this infinite series? The standard way is we can use a generating function, which is a map which maps from the lambda to the summation of lambda power n xm. So this function is still infinite dimensional. However, when evaluated as some lambda, it gives the finite dimensional representation. So similarly, on the high level, the path development of the path X is a map which maps from some linear map M to the summation of M power n, act on the nth level of the signature of a path X. I will give a more precise definition of the path development layer, the path development later. But here the idea is that we will make this linear map M trainable, and we will select the optimal or the useful linear map M, and the resulting the path development is a finite dimensional, and which can be data adaptive. So the path development layer actually has a nice connection with both the recurrent neural network and also the continuous time series model like the neural ODEs. So it has the recurrence structure like the classical recurrent neural network, but in a more simple and principled manner. And besides, it also belongs to the continuous time series model because it can be characterized as a solution to the control differential equation. Therefore, it also enjoys the nice properties of the continuous time series model, like the robustness to the missing data and the irregular sampling. So in the following, I like to introduce the development of path, which is actually the core concept of the rank path theory. So here let capital G denote the finite dimensional Lie group, and the corresponding Lie algebra is denoted by the smaller g. And in the slides, I provide you with a few examples of the matrix Lie algebra. So the GL denote the M by M the set of all possible M by M squared matrices. And here I want to emphasize that the Lie algebra is a vector space while the group is not. So let's consider a path X, which is a continuous path of the bounded one variation. And this capital M is a linear map, which map from RD, where the path takes value to the Lie algebra G. And here we focus on the matrix Lie group. The path development or the Catan developer of X on G under this linear map M is the solution to this linear control differential equation, where the starting point Z0 equals to identity, or in this case, the identity matrix. And the multiplication here, you could regard it as a matrix multiplication. So because the right-hand side of this equation always lives at the tangent space of the group evaluated as ZT. Therefore, the solution ZT lives in the corresponding the group capital G for all possibility. And we call the capital T the ending point of the path development as the development of X under M denoted by this D M of X. And here capital M serves as a role as the lambda in the generating function for the classical case. So the definition of the past development might seem a bit complicated at the first glance. Let's have a closer look at of this object. So for the simpler case, when x is the linear path, then the path development actually can be calculated explicitly. So the development path of x on the M is nothing else but the matrix exponential of the linear map M acting on the increment of the path. And also the path development has a very nice mathematical properties. For example, the multiplicative properties. So if you have the two paths x and y, the development of the concatenation of the path x and y is actually the product of the development of x and the development of y. So this property allows us to compute the development of any piecewise linear path explicitly. And also I want to emphasize that the path development lives on the manifold instead of a certain vector space. So in the slides, I gave you an example of the hyperbolic development. And for this example, X is a two-dimensional piecewise linear path, which is plotted on the left panel of this figure. And here we consider the linear map capital M defined in this way. Then we plot in the figure on the right panel, plots the last column of the development of x from time 0 to t. And here you can see that the development actually lives in this hyperboloid space. So there is a well-established link between the path development and the signature. That is given by this theorem. So the development of the path x on the M is the canonical linear extension of M acting on the signature of the path. So the canonical extension of M tutor is defined in this way. So let's EI denote the basis of the RD. Then this extension of M tutor is a map, linear map, which maps from the tensor algebra space of RD to the GL, the algebra. And because this is a linear map, we only need to define the M tutor acting on the basis, which is the M tutor acting on the EI1 tensor onto tensor EIK. It's the matrix multiplication of M of EI1 onto M of EIK. So roughly speaking, and here then you can see that the development and the signature relationship can be explicitly represented by this M tutor map. So this is a table to summarize the properties of the signature and the development. So both feature of the time series has a multiplicative property and the time invariance. So if you give a different time parameterization to your underlying path, the corresponding signature or development will remain unchanged. And also when you choose the development the Lie group to be symplectic group or unitary group, the corresponding path development has a universality as well as the characteristic property, just like the signature. However, the development is trainable. So the linear map M will become the model parameters and learn from the data. However, the signature feature is a deterministic feature. So in the following theorem about the characteristic of the development under the symplectic group, highlights the dimension reduction benefits of the development in compared with the signature. So here, if we have the tensor, it have the element X lives in the tensor algebra space, the case level is non-zero. Then we can find the linear map M, whose domain is in this Lie algebra with a matrix order M. As long as this M is larger than the maximum 2n k over 3, then the M tutor of X is non-zero, so it can separate the points. So that means if we have the two signatures differ at the case level, we need the development matrix order at most the quadratic in terms of k. However, the dimension of the truncated signature up to degree k grows geometrically. That demonstrates the potential dimension reduction benefit the development offer. And in our recent work, we provide alternative constructive proof for the characteristic of the unitary development. Okay, so now we are ready to propose the proper definition of the path development layer. So the path development layer takes the discrete time series X as an input, and the output is the matrix or the sequence of a matrix Z. And the output Z is defined in a recursive way. Z at time n plus 1 is given by Zn times the matrix exponential of m theta act on the increments of X between time n to n plus 1. And the Z0 is given by the identity matrix. So here the theta is the model parameters of the path development layer, and this linear map m theta maps from the RD to the corresponding Lie algebra. So here you can see that the Zn is nothing else but the path development of the piecewise linear path X up to time m. And from this formula, you can also see analogy to the recurrent neural network. So Zn can be viewed as the hidden neuron of the recurrent neural network at time m. However, the recurrence is more principled, and there is no complicated neural network involved, but only matrix exponential and multiplication. And so by the definition, it's easy to write down the forward evaluation of the path development layer. And to enable the usage of the path development as a layer to be inserted in the general neural network, we need to implement the backpropagation of the path development layer. So essentially, we need to find how can we numerically optimizing the model parameters of the path development layer. In other words, how can we calculate the derivatives of a certain scalar field per psi composed with a development layer d theta. And because of the recurrence of the development layer, it's natural to use a chain rule to derive such gradients. However, one thing we need to take care is that the output of the development lives on the Lie group. So to enable the chain rule, we need to use the optimization method on the manifold, so-called trivialization. So trivialization is defined as a surjection map, which map from RD to the Lie group G. So the original optimization problem, minimizing f of x when x is belongs to G, can be reformulated as a minimization problem of f composed with phi. And here you can see that using the trivialization, we translate the constraint optimization to the unconstrained the problems. Then we can use the standard gradient descent on the Euclidean space to enable the optimization. And this theorem shows a recursive structure of the differential of the development layer at the end, which is given this formula. And by taking advantage of the link between the differential and the gradients of the matrix exponential, we have this recurrence formula for the gradient calculation of the development layer. And I provide you with a pseudocode of the backward path of the path development layer. And here we implement the development layer using the PyTorch, and it can be used conveniently, just like the other neural network layer. So here you only need to specify the batch size, the time dimension, and the feature dimension, and choose the matrix order as this hidden size, as well as the Lie attribute you want to use. Then you can pass your input with those parameters. You will using this so-called development underscore layer function, you will get the output, and you can also do the fabrication. So in the following, I'd like to show you the numerical experiments of the past development on various tasks. So let me start from the time series, examples of the time series and the sequential image modeling tasks. So we consider the two types of the development layer-based method. One is a vanilla development layer, and the other one is a hybrid model, which is composed with LSTM followed by the development layer. And to benchmark our method, we consider various baselines. That is the signature models, IM models, which include the LSTM, and also the exponential IM, which incorporating the matrix Lie group, as well as the continuous time series model like the neuron CDEs. Moreover, we also compare our model with the SOTA models like ZK convolution, flex TZN, and so on. The data set we use here include the character trajectory data set, speech commands data set, as well as the 3 sequential image data sets. So the speech commands data set has a path dimension 20, which is example of the high dimensional time series. And so let me first show you the comparison between the path development layer and the path signature. So here we use a linear model on both the development and the signature. And we plot the test accuracy against the feature dimension. So all those tasks are the classification task. And here you can see that to achieve the similar accuracy of the signature of the depth 3, the dimension of the development, the matrix order required to use for the past developments is about 30, which resulted in the feature dimension like 1000. However, the corresponding feature dimension of the truncated signature is it's about the 9,000. So here you can see the quite large dimension saving provided by the development over the signature. And in the slides, this is the summary of the accuracy comparison on those data sets. So here you can see that the LSTM with the development under the SO group can achieve very competitive result to the SOTA methods, and significantly output the baseline, whether it's the signature based or the continuous time series model or the IM model. So you may see so the LSTM plus development can achieve the comparable sort of results. However, it still have the big performance gap on the Sapphire 10 data set. Except for the Sapphire 10, if you look at the accuracy comparison of this hybrid model with a SOTA model, you will find that although the accuracy performance might be slightly less, about 1%, but the number of the parameters our model only has utilized the 1/4 model parameters. And we also tested the robustness of the proposed method. So the continuous time series model, like the NCDEs, has the strengths in the irregular sampling and the missing data. And here we consider the case that we randomly throw out a certain percentage of the frames on the tested data sets, or we change the sampling rate and test how the tested accuracy changes. And here you can see that our hybrid model achieves the best robustness among all these methods, which demonstrate the superior robustness to the missing data and the variable sampling rate. And also the past development is very useful to enhance the training stability of the LSTM. So here you can see that without adding the development layer, the LSTM training trajectory is not very stable, and it actually the performance of LSTM depends significantly on the choice of learning rate. That means unless people do extensive hyperparameter tuning to the learning rate, the LSTM's performance might not be very good. However, by adding the past development, especially the special orthogonal group, the training stability increases significantly, and also the test accuracy, it doesn't depend on much on the choice of the learning rate. And compared with the special orthogonal group, and so here we choose the special orthogonal group and the compact symplectic group used for the development, and SO group always show the better performance. That's actually has a theoretical justification, because when using the SO group, the differential of the development has the isometry, so it preserves the certain norms of the derivative, which helps with the training stability and alleviate the gradient vanishing and exposure issue of the LSTM. And secondly, I'd like to show you how the path development are useful for time series on the constraint space. And here we consider the regression problem of predicting the Brownian motion on the sphere. And here the driving path is the discrete Brownian motion on the unit 2 spheres. And the task is to predict the future Brownian motion trajectory from the the task is to predict the Brownian motion trajectory from the given driving random work. So this is the sequence-to-sequence supervised learning problem. And here you can see that if one uses LSTM or the exponential IM, which utilize a matrix Lie group, but not in the same way as we did, the estimated outputs may not live in the correct space. However, by using our hybrid model, we can ensure that the estimated output lives in the sphere, which significantly enhances the accuracy. And also, this is another example about the using the development to estimate the time series on the constraint space. So this is the task of n-body simulation. So instead of estimating the location of the particles directly, here we use the development and reformulate the problem of estimating the transformation matrix of the future location of the particles. So here the SE group is well suited to this case. And you can see that by using the appropriate choice of the group, our hybrid model gives better performance than the baseline. So how much time do I have?
You still have about 15 minutes.
Okay. So in the following, I like to show you the application of the path development layer for the skeleton-based action recognition. So the task is to predict the action class based on the skeleton movement information. And this is the joint work with my postdoc Lei Jiang, my collaborator Wei-Xin Yang, and Xin Zhang. And motivated by the skeleton-based action recognition, we propose the extension of the path development layer on the temporal graph. So temporal graph refers to a graph whose node feature is a time series. And here we don't require that the time series are equally are sampled at the equal spacing or fixed length. So the G development layer is the extension of the path development layer from the RD value time series to the temporal graph. And it utilizes the path development of the time series in the sliding window fashion. So over each sliding window, at each node, we transform the time series to the path development, which is the static matrix. And the linear map are shared across the node. And by using the sliding window, we the G development layer it actually maps the temporal graph to another temporal graph, but with a potential reduction, time dimension reduction, and the output of the G development at each time t it's the output of the G development module. The node feature is a matrix. So this is a visualization of the G development layer. So in the literature, the convolutional neural network are powerful for the skeleton-based action recognition. So GCN network has a strength in capturing the spatial dependency of the skeleton. However, it's unclear that the graph neural network are the best way to capture the temporal information. And to this end, we use a hybrid model by combining the development with the LSTM to better capture the temporal information. And our strategy is to use the GCN to extract the spatial information while using our proposed development LSTM hybrid module to extract the temporal information. And this framework can be used for the general GCN on the temporal graph. And here we provide the performance comparison of our proposed method. And in the table, I also provide you with the list of the SOTA models on the two large-scale action recognition dataset, NTU 60 and NTU 120. And here you can see that our proposed method achieved the comparable SOTA results on those two benchmarking data sets. And if we look at the robustness comparison, our proposed model significantly output the SOTA CTR GCM models. And also we show that by adding the development, we have the better robustness of the action model in comparison with the GCN LSTM. So the robustness test we conducted is given as follows. So we test how the accuracy change if we randomly dropping or inserting the certain percentage of the time frames. And those two plots show the accuracy performance variation when we randomly dropping some joint number in each frame. Either use this plot to correspond to the zero imputation, and this one is to do the is to use the last value imputation. In either case, we show that our proposed model has a better robustness compared with the backbone CTR GCN and the GCN LSTM. So in conclusion, the past development is a general and trainable layer for the sequential time series data. And it's the data adaptive alternative to the past signature, bringing the massive dimension reduction, in particular for the high dimensional paths. And the LSTM with the development can achieve the result on the moderate time series data set, and they show the superior robustness to the irregular time sampling, changing the sampling speed, and also stabilizing the training process. Moreover, the group structure output of the development may be instrumental in predicting and simulating the evolution of the evolution of the sequential data on the constrained space. For example, the rigid body movements and so on. So and also, I want to mention that we applied the past development on the generative model for time series generation. So intuitively, if one regards the signature of the path as the monomials on the path space, and then the expected signature serves as the movements, serve the role as the movements of the stochastic process. And likewise, the expected development actually the expected development of stochastic process under the unitary group can be viewed as the characteristic function of the distribution of this stochastic process. Therefore, motivated by this, we use expected development. We call it a path characteristic function to design the discriminator for the distribution of the general to stochastic process. And we can apply it on both hypothesis testing of the stochastic process and also the synthetic time series generation, which achieve quite good performance on the empirical data set, in particular financial data set. And in terms of the future work, we will be interested in extending the linear vector field to the nonlinear vector field. And also, the past development has the backpropagation can be also implemented in the adjoint method, which is memory efficient. If we regard the past development as the extension of the neural ODE. Moreover, I will be interested exploiting the application of the past development on the sequential data with inherited symmetry, as I mentioned before. For example, rigid body motion or the stochastic process on the constraint space, such as the sphere and so on. So I think I'd like to stop my presentation for now. If you are interested in knowing more about the research of my research group, there is a link on the website. Yeah, thank you very much.